In this video I want to tell you about the distributed electron, an example of which is shown here. Each of the dots that make it up represents a rotating feature. The size of the dot gives its mass and angular momentum, while the colour gives its phase. Incidentally, this structure is rather coarse-grained. In a structure like the hydrogen atom, there will be many millions of these dots. The sum of all the angular momenta turns out to be h bar upon 2. In other words, this theory replicates the findings of normal quantum mechanics, while giving huge insights into its many puzzling features. In this video, I'm going to give a whistle-stop tour of the theory leading to these structures. The subject is covered in depth in the video series The Road to Quantum Reality. As you clicked on this video, you obviously have an interest in quantum mechanics and will probably have a knowledge of its normal interpretation in terms of probability clouds governed by the Schrodinger equation, subsequently refined as a Dirac equation. You will have been taught that these waves are not real, but merely mathematical functions which tell us everything we can possibly know about what can be measured and what will happen next. But having a knowledge of something is not the same thing as understanding it. As Richard Feynman said in his book QED, "While I am describing how nature works, you won't understand why it works that way." What you might not be aware of is that the current interpretation of quantum mechanics was never a slam dunk. Schrodinger himself originally thought his wave function would describe something real, such as a matter density, rather than something merely probabilistic. Born was drawn to the probabilistic view because scattering experiments appeared to match a model having the whole particle at some single point. Schrodinger was never able to suggest a viable alternative to counter the probabilistic point-particle view, and it is now baked into quantum mechanics. For example, if you have looked deeper, you might have come across the path integral theory of Feynman, with its perception, at least mathematically, of a probabilistic point particle following all paths at the same time to calculate some probability of electron leaving one point and arriving at another at a fixed time. And of course, Feynman was correct. No one is ever going to understand such a concept, for the simple reason that it doesn't make any sense in descriptive terms. What it does is provide a calculation method which amazingly can be made to give exceedingly accurate results. Okay, let's go. We start with longitudinal waves in some medium which might historically be called an ether. Apart from not knowing what the medium is, this is a very simple and approachable concept. You just have to think of sound waves with their travelling zones of high and low pressure and density. It's a well-known feature of sound waves that if they approach a point in space with their phases and directions correlated, you get vortices formed by zones of high pressure or density rotating around the point. In the theory, I have called these vortices field rotators, or FRs for short. If we were talking about 4 waves consecutively from the north, east, south and west, the rotation is clockwise. If the waves come consecutively from north, west, south and east, the rotation is anti-clockwise. We see that our model already has the potential to encompass 2 spins of opposite direction, and that the potential to quantify the angular momentum exists. We also noticed that for our simple 4-wave model, the FRs repeat themselves in a grid pattern. Now we ask, what would need to happen if we wish to model a particle, such as an electron, as a structure of FRs? The first thing is that the FRs must somehow talk to each other or interact with each other. If an FR is a distributed part of a structure, perhaps containing some element of the mass of the particle, then it has to know its place. It can't just get more intense when it fancied it. Its magnitude and phase are dependent on what every other part of the structure is doing. And it itself is nothing more than the sum of all the contributions it is receiving. We can set this up quite easily if we make one simple postulate. We say that some, presumably small, fraction of the waves forming the FR do not pass straight through, but are absorbed and re-radiated as a spiral wave. You can see in this picture that these spiral waves will tend to reinforce each other along the grid directions, but not in other directions. If you studied physics, you will see a parallel here with Huygens' principle, in which he surmised that every light wave could be deemed to be the source of a spherical wavelet, and the next position of the wavefront was given by the tangent of all these wavelets. Or indeed Feynman's approach, which makes a similar assumption, but for probability waves. The main difference is that we are saying that the locations of the secondary generators are discretely spaced, and the generated wavelets will be outgoing spirals, with the direction of the spiral indicative of the rotation direction, the spin, if you like. And our waves are real physical waves, just like sound waves, not conceptual constructs. But why don't the structures just evaporate? How could a structure be stable? Surely waves are always leaving, carrying energy and momentum with them. In fact, we require that the FRs lose wave energy in this way. We can introduce the concept of empty waves. Remember, the waves we are describing are real waves in a physical medium. They carry energy and momentum just as a sound wave would. They are empty because they are not systematically in what we might call phase direction correlation with other waves. So they do not form FRs with angular momentum and fixed mass. They are quite capable of coming alive again if they do subsequently find themselves in such a relationship. In fact, because all these empty waves will fill space, forming what we might call a stochastic field, it is certain that such interactions must be occurring all the time, forming what we might whimsically call fragments. They would not last, but their duration would presumably have the characteristics of mass. Perhaps they should be considered as candidates for dark matter. Anyway, let's summarise these postulates. The mechanism being proposed is that FRs will have their amplitude increased by the stochastic presence of empty waves having the correct phase direction characteristics. Perhaps this is better visualised as a resonance effect. Obviously, if this postulate works out and gives sensible results, the process would warrant much deeper analysis. If you are not happy with this, then it can just be postulated as a mathematical procedure for now, in the same way that Feynman's rules are just mathematical postulates without any real physical interpretation. As a result, each FR will act like a source within the structure, which for a stationary state must exactly balance the losses via empty waves. We need to quantify this gain. We can postulate that the gain will be proportional to the current amplitude of the FR and dependent on the local strength of the stochastic gain field. Our next problem is how to handle the concept of potential. We don't have a point particle on which to hang a charge, whatever a charge is, so we can't just apply Coulomb's law. But we do need some equivalent. After all, we know that what is currently explained as charge does indeed control the shape of the wave function in regular quantum mechanics. So something equivalent must control the shape of any structure we generate. We only have one parameter, the local strength of the gain field. So we postulate that the local gain field can be modified by the nearby presence of other structures, such as the proton, in which case the modification will have the same mathematical shape, that is, 1 upon r, that the Coulomb potential has. That is, the stochastic gain will be low close to the proton and gradually increase with distance as we move further out. Other potentials, such as the simple harmonic oscillator potential, would be modelled by the appropriate mathematical form. We are left with just one parameter. What should we choose for the ratio of amplitude to re-radiated spiral wave amplitude? It's a dimensionless parameter. Quantum mechanics has one of these, of course. It's alpha, the 1 upon 137 factor, about which you will find hundreds of YouTube videos. We might as well use this value. It will turn out to be a fitting parameter which will enable us to scale our model to standard quantum mechanics. It controls the size of the structure. That's it for the postulates. Now all we have to do is the calculations. These are conceptually simple, especially if we constrain ourselves to stationary structures, by which I mean structures which do not change their shapes in time. They're not really fully stationary because the FRs are rotating, but the structure is not changing. A particular FR will have the same magnitude for all time. With this proviso, we set up a grid of FRs. And remember, the grid is a natural form for our toy 4 orthogonal wave model. And then we calculate for each FR how much every other FR is adding to its amplitude via their outgoing spiral waves. It would seem that we need to take both the direction from which the wave arrives and its phase on arrival into account in evaluating how much it is contributing to the amplitude of the target FR. In fact, as explained in the detail videos, it turns out that these two factors cancel out, and all we need to consider in calculating the arriving phase is the distance from source to target. Thus, despite us calculating for spiral waves and rotating FRs, we end up doing the same summation as Feynman would for spherical waves. This must surely give pause for thought about why Feynman's methods work. There is one difference though. Because we are calculating for physical waves, we have to allow for their physical amplitude to fall proportionally to the distance from source to target. Feynman is dealing with probability waves and amplitudes and does not include such a fall-off. Also, he is considering every point in space as a source. But in using the Feynman sum, such as in his derivation of the Schrodinger equation, mathematical techniques are used to suppress contributions from more distant sources. I'm afraid it is beyond me to evaluate whether the two approaches are in fact identical. Our calculation proceeds as set out in this green equation. For each FR being treated as a target, let's call it psi I, we take the sum of contributions from every other FR, say psi j, which we calculate by multiplying its amplitude by the factor mu ij, which includes alpha and all the geometric aspects such as the distance and relative phase. The sum is then multiplied by the local gain factor, which of course includes any variation due to the presence of other objects such as the proton. And for a stationary state, this must take us back to where we started. As previously noted, the addition process will involve a lot of constructive and destructive interference, like Feynman's little arrows. Following on from this process, we arrive at what is essentially a large set of simultaneous equations, one equation for every FR in the structure. We can best express these as a matrix equation. Fortunately, a large set of simultaneous equations can be solved using matrix methods, which can be handled very efficiently on a computer, provided there are not too many FRs involved. Here, the matrix M contains all the geometric factors mu ij, and also the gain multipliers along its diagonal. In effect, the matrix equation is just saying that the psi values, if multiplied by m, give us back the same psi values multiplied by some constant number, lambda. The results obtained are a set of eigenvalues and eigenvectors, but maybe it is better to call the vectors eigenstructures. The structures are a set of complex psi values, one at each point on the grid. You have already seen these plotted for one particular structure in the introduction. You may have seen a very similar calculation being used to solve the Schrodinger equation using finite difference methods. One big difference, however, is in the interpretation of lambda, the eigenvalue. Lambda can be a complex number, and if it contains an imaginary part, it means that the phase is changing. If you were solving the Schrodinger equation, you would say that the rate of this phase change is the energy of this wave function. You convert the frequency into energy using E equals h bar omega. We cannot view it in that way. For us, there is only one possible value for lambda, and that is 1. It's a stationary state. It must be that the value of psi is exactly the sum of all the contributions multiplied by the gain. This means that the energy differences between structures, which we know are predicted correctly by quantum mechanics, must be somehow factored into M itself. We can show that this is indeed the case, and the way it arises is very intuitive, but you will have to follow the main videos to see how it is done. Unfortunately, the not too many FRs constraint turns out to be quite severe. It means not too many at all. In 2 dimensions, the work has so far been restricted to 80 by 80 grids, while in 3 dimensions a radius of about 27 is the limit. It has not thus far been possible to calculate comparative results for the Coulomb potential, because this potential tails off with distance too slowly, and structures are very extended, albeit with very low magnitudes. It is possible to calculate for the simple harmonic oscillator potential, because this rises very quickly with distance and suppresses magnitudes further away from the centre, thus keeping all FRs with significant magnitudes well within the boundaries. The simple harmonic oscillator potential structures share many features with the Coulomb potential ones. Actually, they are a lot more simple. Okay, this is an overview type of video, so let's see what we get. Here are some 2D structures. If you know a bit about quantum mechanics, you will recognise them as Schrodinger-like shapes. They are raw structures because the software seems to find superpositions of degenerate states with contributions from each pretty much at random. For example, the two states in the second row could be represented as base states with two distinct peaks, or as angular momentum states with a circular density. It is possible to recalculate the pure states from those found, and this is done to calculate orbital angular momentum later. The two shapes found here are superpositions of these two possibilities. If we zoom in, we can see the actual FR magnitudes and phases. But zooming in reveals a rather startling finding. The phases of FRs at alternating locations on the grid differ by approximately pi radians. This was initially an unexpected result, but it is in fact the reason why the structures conform with results from the Schrodinger equation. There is a video on how this happens in the Road to Quantum Reality series. It is also the reason why electrons obey the Pauli exclusion principle, and indeed the reason that they are fermions. Here we see structures 2 and 3 after processing them to put them in angular momentum form. The magnitudes are indicated by the colour and the phases by the directions of the arrows. The two structures have identical magnitude profiles, but the pattern of phases looks quite different. The phase alternation rather conceals the other underlying phase variation across the structures. It can be suppressed to clean up the pictures, such as in this one of structure 5. The underlying variation is very beautiful and clearly meaningful. Here are some 3D forms, and remember that these are very highly constricted in size by very large potentials so that we could do the calculations. Again, the phase alternation is present but has been removed for clarity. As previously mentioned, in these figures the size of the dot is indicative of the magnitude and the colour is the phase with alternation suppressed. These are just the same forms as predicted by the Schrodinger equation. Not only are the structures the same as the Schrodinger ones, but the energies have the same form, being equally spaced. There are more details about this in the main video series. So this is the distributed electron. It is exactly the sort of thing Schrodinger was looking for. The wave function is describing something real, namely the magnitude and phases of all the discrete FRs which go together to form the stable structure. The imaginary feature, which so troubled Schrodinger in the early years, is present because it is the best way to keep track of the phases of the FRs. Schrodinger's equation is embodying the harmony of the phases principle for our discrete FRs. And if we take the square of the magnitude at each FR, we find we can equate it to part of the mass of the electron structure. We just sum up all the square magnitudes to get the total mass. The difference between our interpretation and the standard one is that we see each FR as a small fraction of the mass, while the normal interpretation says that each point of the continuous wave function gives us a probability of finding the whole mass at that point. But we haven't lost the probabilistic aspect entirely. If a measurement of position is made, the normal interpretation gives a probability for the particle to be found at this point. We will say that the probability for the structure to be collapsed to a certain point, for example, to be absorbed by an atom on a photographic plate acting as a detector in a twin-slit experiment, this probability will be proportional to the fraction of the mass at this point. Both prescriptions work mathematically, except that we can allow the mass to change due to relativistic effects. Now we come to a key feature of the distributed electron model. Actual quantum particles, such as the electron, are known to have something called spin angular momentum. If you have studied physics or followed enough YouTube videos, you will know that it is not possible to explain this using the probabilistic point-particle model. There is just nowhere within the model to put it. It is so-called intrinsic. The distributed electron model does have somewhere to put it. We have a myriad of rotating FRs, each with an angular momentum. We can sum these to give the total spin angular momentum. The actual calculation is done in the spin video in the Road to Quantum Reality series. Here is a quick summary. The radius of the centre of mass of each FR turns out to be fixed by the geometry of waves, and the rotational frequency and wavelength are fixed by the mass of the electron. The result is that the spin is h bar over 2. Not only do we have somewhere to put it, but it has the correct value. In other words, spin is not intrinsic for the distributed electron model. Had Schrodinger found this model, he would have been in a position to predict spin angular momentum. How about orbital angular momentum? Let's go back to these two structures. The pattern of the phases is obviously important. These plots include phase alternation, which we should of course suppress before attempting to calculate the orbital angular momentum, and that's easily done. In normal quantum mechanics, the momentum operator is given by this equation. How motion is understood in real wave quantum mechanics and how it leads to special relativity is addressed in this video. The key finding is that it is the velocity of a structure which is related to the phase gradient, or k. Let's go back to this quantum mechanical operator equation and recall that it is based very specifically on the probabilistic point-particle model. This means that it is deemed to apply to the whole mass of the point particle. Even if the gradient term was actually giving a velocity, it could be used to infer the momentum because of the assumed fixed mass whose motion it was describing. Incidentally, this leads to some very weird interpretational issues. Since the angular momentum is conserved and is a Lorentz invariant, the model says that a point electron very close to the nucleus would have to be moving at close to the speed of light. This has led to the tentative prediction that very heavy elements might not be possible because the innermost electrons would need to be moving at the speed of light. Anyway, returning to our interpretation of the standard momentum operator, we cannot use it in this way because the mass is distributed and the phase gradient is varying across the structure. We would need something like this expression. In words, we calculate that the momentum is the product of the local phase gradient del phi and the local mass at each FR, psi star psi, summed over all FRs. Applying this procedure to structures 3 and 4, we get the momentum vectors at each FR shown in these figures. They have a plug hole appearance. To calculate the orbital angular momentum, we can resolve the arrow vectors into axial and radial components. Summing the axial components gives us the values shown here, essentially 1 for structure 3 and 2 for structure 4. And of course, these are the values quantum mechanics predicts. The orbital angular momentum is quantized in integer multiples of h bar. Remember, we are working in units with h bar equals 1. As a check, let's apply the same procedure to structure 5, which should have no orbital angular momentum. And it doesn't. These findings give us a great deal of confidence that the distributed electron is reasonable and is consistent with the findings of regular quantum mechanics, without requiring crazy interpretations of the point electron having near luminal velocities. But what is actually moving to give rise to orbital angular momentum? The FRs are not moving. If they were, it would completely destroy the phase harmony between them. We may have got rid of one crazy interpretation, but we haven't really replaced it. We have merely conjectured a mathematical procedure which gives the correct results. Well, maybe not. Perhaps it is wave energy itself which is flying around the centre for structures 2 and 4. In special relativity, we are aware that mass and energy are interchangeable via E equals mc squared. So a flow of energy is equivalent to a flow of mass, and this has momentum. These relationships are all encapsulated in the momentum 4 vector of special relativity. But the answer to one question opens the door to another. What is the radial momentum all about? It implies a momentum flux inward from areas of high potential to areas of low potential. This is still being worked on, as indeed is a Lagrangian foundation for the model. So let's leave it there with the following summary. The distributed electron is able to replicate quantum mechanics in many ways and can explain many of its otherwise puzzling features. It is not yet a complete theory, but it has opened the door to a change in the way quantum mechanics is understood and interpreted. But there is still a lot to do, and unfortunately I am too old to see it through, so why not join in? Thanks for watching, if you managed to get this far, and don't forget to like, subscribe and share with your physicist friends.